Greetings and welcome to the lab introduction to what we call the Hydrogen Spectrum Lab. This is a fun lab that you'll get to see essentially a fancy type of light bulb. And I know that sounds weird, but light bulbs actually have the same principles as the hydrogen spectrum and other things we're going to look at in this lab. It's pretty cool. This is a deviation from normal chemistry. People oftentimes think that chemistry is all about adding one chemical to another and seeing what happens. This particular lab is mostly about light and how the electromagnetic spectrum can help chemists to make transformations possible. But of course, you have to understand where all this stuff is coming from. So this is a fun lab, and I think you're going to enjoy it. Let's talk about what you're going to see. So in this lab, you will actually observe what's called the sharp line spectrum for hydrogen. And you can think of these sharp line spectrums as being a type of fingerprint. And each element has its own fingerprint, its own sharp line spectra. And this is what astronomers use to identify elements in other planets and other suns, which we couldn't visit using in our lifetime, stuff like that. Bohr was the first one to kind of figure out a little bit, at least, what was going on. So we're going to use the Bohr model to extensively look at hydrogen and to understand, for example, where the wavelengths come from, and also do some conversions of wavelength to frequency, frequency to energy, and much more. So it's going to be kind of cool. You're actually going to look through what's called a spectroscope to see the hydrogen spectrum. It should be pretty fun. So let's talk a little bit about what you will see in this lab and also where the things that you do see will come from so you can better understand what's happening. Greetings and welcome to the Chemistry 220 lab, the atomic spectrum of hydrogen. This is one of my favorite labs. Normally, if this class is meeting or would meet in an actual lab room, this lab is quite different from the other labs. We don't really mix chemicals and measure grams and milliliters, stuff like that. This lab is all about light and the energy essentially created from a hydrogen discharge tube. A discharge tube is basically a fancy name for a type of a light bulb. Light comes out when electricity is added to it. So it's pretty cool. We'll also get to talk about the Bohr model of the atom, stuff like that. So without further ado, let's see what this lab has to offer. This lab is basically measuring and interested in what's called the sharp line spectra for hydrogen. And to understand where the sharp line spectra comes from and what it is, we're going to use the Bohr model, which works really great when it comes to hydrogen and single electron things. In the actual physical lab, we would have observed the hydrogen spectrum directly, and I'll talk about that using something called a spectroscope. In this online lab, we'll see kind of virtually how it works out. It's not quite the same, of course, but it's still pretty cool. And if you do get a chance to do this lab in an actual experiment sometime, it is pretty cool. This picture in the lower right shows essentially like a type of a light bulb, and light bulbs are probably what you're using right now in wherever you're listening to this video, watching this video. It's really nice to have the light, and of course revolutionize society, blah, blah, blah. However, all lights, if you take them and pass the light through a prism is essentially a way to separate out the different wavelengths. And maybe you've seen this on a hot day. If there's like a prism running around, you'll see like a rainbow. All right, the rainbow essentially is splitting the many components of regular light into all the different pieces. So it's a pretty cool thing, and all light bulbs are like this. Now, normal light bulbs, when you put them through a prism, you just see the cool rainbow, and the rainbow is pretty awesome, all right? However, we're in this lab using a special kind of a light bulb, and our special light bulbs, if you will, have just one element inside. So the primary light bulb, if you will, we're going to use in this lab is a hydrogen bulb, and they call it a special kind of an emission bulb, but it's basically the same kind of thing. And if you have just one element inside and you place it through a prism, you're going to see like specific, very sharp lines, and it's really a cool thing. This every element has like its own fingerprint of lines. All right, hydrogen we're going to see has these 4 sharp lines. Some elements have more, some have less and stuff, but they're at very specific wavelengths. And a long time ago, when people started doing this, they were like, whoa, this is really cool, and they started measuring them and stuff like that, and they know them to a lot of accuracy. These sharp line spectra are critical for astronomers because astronomers can't even get to like our sun, and they can measure the composition stuff of different things by looking at the sharp line spectra for different things that are a long ways away. So it allows you to analyze the composition of things without actually having it in front of you, which is a really, really kind of neat thing. Of course, we're not astronomers, we're chemists. We're going to look at it from different perspectives, but hopefully you can see the utility. In forensics, of course, DNA analysis has provided all kinds of cases being solved through DNA, and only one person can have it. Well, you can think about this as a kind of a DNA for elements. It's a series of sharp lines in a spectrum, all right, that are only for like one particular element. And I can't underestimate how important it is and how cool it is too that this thing exists. Nobody really understood, though, like why each element has this sharp line spectrum pattern, and why is hydrogen different than helium and stuff like that. They could measure them, but they really didn't understand. So Bohr came along with a model, which came a little bit out of the blue sky, but it was still pretty cool. And he basically said that, all right, if you have these systems, there's going to be these discrete energy levels, and he gave them the symbol N. And N, by the way, is one of the quantum numbers that we're talking about, or we'll talk about in lecture, depending on where you are. And these energy levels start at N equals 1, which is the level closest to the nucleus. And then they go 1 to 2 to 3 to 4, et cetera, et cetera. And as they get far bigger in N, they get farther from the nucleus. So there'll be different energies and stuff like that. Bohr was really cool because his model still works today really well for hydrogen and things with single electrons. When you get to elements, though, with more than one electron, for example, carbon or sodium, things like that, then you need a different model. In the lecture, we're going to talk about what's called the N plus L rule, where the energy is dependent on more than N, and that's where that kind of stuff comes from. But for here and now, all right, Bohr's model works really great for hydrogen, and that's what we're going to look at. We're going to look at the hydrogen emission spectrum and see how this all works out. And again, realize that if you get past hydrogen, then you may need other kinds of rules, but for hydrogen, it works out really well. So in the Bohr model, all right, you've got all these energy levels. And here in the lower left side, this is like N equals 2, 3, 4, 5, 6, etc., etc. And electrons start usually at a lower energy level. So the yellow line on the far left, the electron is starting at N equals 2, and it's jumping up to the highest level, which is N equals 6, all right? Now, to go from a lower energy to a higher energy, you have to have energy put in. This is an endothermic transition. You need energy to have it happen. And if you have an electron going from a lower N to a higher N, it's something that needs energy to have happen, where it's something that's endothermic. They call this kind of transition an absorption line. And absorbance spectroscopy, or absorption, is a real powerful tool. It's based on the ability of electrons to jump from lower energy levels to higher energy levels, and it's really, really cool. But really, this lab is about the opposite process. Like after a while, that electron, which was at N equals 6, is going to go back down to the N equals 2, that kind of purple line right there on the far right. If you have an electron going from a higher energy level to a lower energy level, energy will be given off, which is exothermic, and these are called emission lines. So in this lab, this is an emission line analysis, all right? We're looking only at electrons that start at higher N and go to lower N, the exothermic. And this is what happens in a light bulb, all right? When the energy that comes off is from an emission spectroscopy. All right, the electricity that goes through excites the electrons from lower N to higher N. You'd have some kind of absorbance line, and then after a while, those electrons relax back down. As they relax, energy is given off, the light we use from the light bulb, the emission lines. So it's pretty cool. So to summarize what I just said, absorbance is going from lower N to higher N, and emission is going from higher N to lower N. We're focusing here on the emission lines, higher to lower Ns. They're exothermic, so you can see something, all right, which is kind of cool, pretty fun. The electrons are just, if you will, relaxing from higher end levels to lower end levels, and that's what we're going to look at. If you studied already the stuff in chapter 6, we talked about how the energy of a photon equals h nu equals hc over lambda. And let's just review real faster what this is all about, because light is a type of electromagnetic radiation, and so these kind of things will apply. So the E here is just the energy of a photon, the smallest piece of light, and the units for that are in joules. And then H, which shows up a lot, H is Planck's constant, 6.626 times 10 to the minus 34 joules seconds. H is really important when it comes to energy. Nu, which looks like kind of an italicized V, is called the frequency. Frequency represents how many waves go by per unit time. Since the unit of time is usually seconds and stuff, sometimes it's referred to as an inverse second. You can think about that as number of waves per second. That's a cool way to think about it. Hertz, Hz, is the unit that equals 1 over a second. So if you don't want to write the little s minus 1, just write hertz and you're good to go. C is the speed of light, 2.998 times 10 to the 8th meters per second. And if you want to turn energy into a wavelength, you will need that. Wavelength is the literal distance from where the wave starts to where the wave stops. So it's always going to be in some kind of length unit. Nanometers is very common, but we're also going to use wavelength in meters. In addition to the energy of a photon, which would be like joules per photon, it will sometimes be nice to think about the energy in kilojoules per mole. So we need to throw a couple more constants and conversions in. Remember that a kilo of anything is 1,000, so a kilojoule would be 1,000 joules. A mole can be used with Avogadro's. In this case, a mole of photons would be 6.022 times 10 to the 23rd photons. And finally, a nano is 10 to the minus 9, so a nanometer is 10 to the minus 9 meters. We're going to use all of the constants on this particular slide in this lab, so make sure you know these. They will come back. We'll use them here in a little bit. If you go directly from a nanometer wavelength to an energy in kilojoules per mole, there's actually quite a few steps. However, because this is a fairly common kind of field, scientists combined a whole bunch of constants to create this little equation right here. Delta E in kilojoules per mole equals that weird 1.19627 times 10 to the 5th divided by the wavelength in nanometers. So if you have a wavelength in nanometers, you can take the 10 to the 5th number and divide it by the wavelength in nanometers to get the energy in kilojoules per mole. And likewise, if you have the energy in kilojoules per mole and you want to know what wavelength that corresponds to, you can plug it in to get it out. This is going to be super helpful to us as well. There's nothing wrong with going through the individual steps, but you'll see there are quite a few. This is just kind of a one-stop shopping kind of version here where it's really nice. We'll see examples of how this works here in a little bit. In the Bohr model, the energy levels, the N values, have an energy associated with them. And in kilojoules per mole, it's negative 1312.04 kilojoules per mole divided by N squared. So if you want to know what the energy of the N equals 1 level is, then you'd put 1 squared in there, and negative 1312.04 divided by 1 squared would be negative 1312.04. That's literally the energy of the first energy level. So let's use this equation to calculate the change in energy, delta E, for an electron going from n equals 2 to n equals 1. This is an emission line because it's going from higher n to lower n. It should give a negative number, exothermic, and we're going to calculate it here in kilojoules per mole. This isn't actually as weird as it sounds. Well, maybe it's weird, but it's easy. Let's put it that way. N equals 2 and N equals 1. That's what those numbers are right there. And a delta is always final minus initial. So basically this question is saying, all right, find the energy of the final N equals 1 state and subtract from it the energy of the N equals 2 state. And the number we're going to get is the energy in kilojoules per mole. So Final minus initial, in this case, means the n equals 1, that's the final state of the electron, minus the initial n equals 2 state of the electron. And if you do that, negative 1312.04 divided by 1 squared, because that's n equals 1, minus, and don't forget this minus another 1312.04 divided by n squared. 2 squared, of course, is 4. Put this in your calculator. You should get negative 984.03 kilojoules per mole. All right? That's the number. It's a negative number, so it's exothermic. Remember, all emission lines will be exothermic. The delta E's you have would be negative. If you flipped the 2 and the 1s around, so the final state was n equals 2 and the initial was n equals 1, you'd end up with a positive 984.03. That would be an absorbance line. Positive delta E's mean absorbance. So anyway, this is the delta E, the exothermic value of the emission line from n equals 2 to n equals 1. So that electron is going from the higher n equals 2 to the lower n equals 1, and it gives off negative 984.03 kilojoules per mole. Let's convert negative 984.03 kilojoules per mole into joules per photon. Okay, so kilojoules to joules, we've probably done already in the calorimetry, the energies chapter. We can go moles of photons into just photons using Avogadro's number. So if you do this, all right, let's start with negative 984.03 kilojoules per mole. Now, mole is in the bottom. A mole is 6.022 times 10 to the 23rd. So mole on the bottom cancels mole on the top. You'll have kilojoule per photon if you do this first part. And then to turn kilojoules into joules, a kilojoule is 1,000 joules. That cancels out the kilojoules. Throw this all in your calculator. Negative 1.634 times 10 to the minus 18th joules per photon. So that's the energy for one photon in this transition. And again, it's negative, but it's a lot smaller because instead of 10 to the 23rd of these, you've only got one of them. By the way, I do encourage you, by all means, to do these calculations in your calculator while I'm talking about them. You should get these numbers, and if you don't, of course, this would be a good time to email me and see if I can help. If you have a question like this, if you can send me a screenshot of what you're doing, I can kind of look at it and then figure out like why you're not getting the answer. This part right here, dividing by a big number, if you're not careful, you can divide by 6.022, but then your calculator will try to multiply by 10 to the 23rd. So instead of a 10 to the minus 18th, if you're getting a really large number or larger than 1, it's because probably your calculator is trying to multiply by 10 to the 23rd. If you put all of this in brackets or parentheses, that would be one way to keep it all together. You can also use the little EE button, and that's something I can help you with too if that doesn't make sense. Okay, back to your regularly scheduled programming. I'm going to assume that you got the negative 1.634 times 10 to the minus 18th joules per photon value, and you're ready to go to the next step. Because the next step says, let's try and figure out the frequency and wavelength in nanometers that corresponds to that transition. All right, so all of these energies come from waves that have frequencies, so many cycles per second, so many waves per second, and also wavelengths, the distance from where the wave starts to where the wave stops. Now, one thing we need to do before we go any farther is that when it comes to wavelength and frequency, technically you could have negative wavelengths and negative frequencies, but the almost universal convention is to just ignore negative signs when it comes to wavelengths and frequencies. So even though the answers technically should be negative numbers, we're going to follow the convention and just call frequencies and wavelengths positive numbers. All right, so just realize that in the back of your mind. Now, energy equals h nu equals hc over lambda. So let's calculate the frequency first. That's this little person right here. So frequency is going to equal the energy divided by Planck's constant. You want to make sure you use the energy per photon. So you can see I'm using the 10 to the minus 18th we calculated earlier. I'm going to divide by Planck's constant, this number right here. The frequency, 2.466 times 10 to the 15th hertz. And a hertz is again the same thing as an inverse second. So that number represents the, if you will, number of waves going by per second, all right? Or the cycles per second, something like that. Wavelength, we'll use the other part here of this equation. There's a couple different ways, of course, you can find wavelength. I'm going to use this equation right here. So wavelength equals hc over delta E. I'm just rearranging the little equation there I put the arrow next to. So if you do that, Planck's constant, 10 to the minus 34 times speed of light, 2.998 times 10 to the 8th, divided by, again, the energy per photon, you get this number, and that comes out to be this number. That's the wavelength in meters. But you can see here that I wanted the wavelength in nanometers. So to go from meters to nanometers, 1 nanometer is 10 to the minus 9 meters. So I'll take the really small meters, divide it by 10 to the minus 9, and you get 121.6 nanometers. That's the wavelength of this transition in nanometers. Now, you could have also went from frequency to the wavelength using the idea of speed of light equals wavelength times frequency. So wavelength would also equal the speed of light divided by frequency. So you could have taken speed of light 2.998 times 10 to the 8th divided by the frequency here. You'd get the same number of meters, which you could convert to nanometers, whatever. But I really like this meme right here. It's like, woo, that's a lot of math, man. And it's all stuff you can do. And again, I encourage you to go along and make sure you do all of this. But what we've just done is we first found the delta E in kilojoules per mole, and then we turned it into a wavelength in nanometers, which is really, really awesome. However, if you remember, all right, that's the answers that we just found out. If you remember, though, there was that kind of quick and dirty equation where delta E in kilojoules per mole equals that weird 10 to the 5th number divided by the wavelength in nanometers. And this is absolutely a time that you could use it. If you solve for the wavelength in nanometers, then the wavelength equals 1.19627 times 10 to the 5th divided by negative 984.03 kilojoules per mole. So notice we're putting a kilojoules per mole in. We're still ignoring the negative sign. That's no big deal. The wavelength, 121.57. You actually get better sig figs with this value because the constants used to find the 1.19627 times 10 to the 5th used better sig figs than the ones that we usually use, but it's the same thing. And sometimes this is a better way to do it. Sometimes it's better to do it the other way. You can choose which path you want to take, and both of them will come in handy in this particular lab. Okay, at this point, I think it's time for a video. I'm going to try and show you a little bit as to what it will be like in the lab. This won't be the best video because the equipment we use will be different, but you'll at least get an idea of what to expect and how to see it. If you have questions on this or anything else, please let me know. I'm definitely here to help you. Enjoy the video and have a great day.